Today I'm talking about inductive definitions, which is one of the few topics that has something to say to all of the main proof assistants. I guess historically it's kind of interesting that in the early 90s, people were interested in the calculus of constructions, which led to Coq. But at the time, this calculus was too weak to do more than do certain interesting little examples, but it had some really serious deficiencies. And it was the discovery of the power of inductive definitions. And you have to give Christine Collant credit for figuring out how to add it to the calculus to give us what we now see as the calculus used in Coq and Lean. That made it a powerful system that could, where one could formalize a great variety of things. Other people saw this, and pretty soon they were copying the idea in their own systems. Now, I should say, in the case of Coq, they had to actually extend the calculus to give themselves a stronger calculus, whereas in the case of higher-order logic-based systems, it's merely a matter of proving the necessary, fixed point theorem and doing some work to make this easily available to users. So what we're going to see, well, inductive definitions aren't necessarily that understandable to everybody, so I'll begin by saying what they are, then how they are used, and then kind of to fill out the lecture, I'll talk a bit about some other stuff, about some automation that you should all know about. So first, the idea of defining a set inductively. It's quite natural in mathematics. Maybe I chose here a slightly too elaborate example. So the simplest example of an inductive definition that one could come across is simply the set of natural numbers. We say 0 is a natural number, and if n is a natural number, then a thing I call successor of n is a natural number. That already gives you infinitely many natural numbers. And finally, you say there are no other natural numbers. This last thing being essential to, shall we say, cut down the set of natural numbers so that to include only things that are either 0 or successor of another natural number. And this final thing, there are no other natural numbers, is where the induction rule comes from. So that is the single and most obvious notion of inductive definition. Now what I have here we're assuming we have the natural numbers already, and indeed we're assuming we have even addition and 2 already defined. So, and one does often in mathematics use inductive definitions not merely to create fundamental sets like the natural numbers, but to describe interesting subsets. So here, the set of even numbers could, this is not usually how you define a set of even numbers, but never mind, could be defined as saying 0 is even, and if n is even, then so is n plus 2. I guess to be precise, this is the set of even natural numbers, because there are no negative numbers here. And of course, the negative numbers can in fact be even. Now, when you see the form of these inductive rules, that is to say, 0 is even, or if n is even, then n plus 2 is even. If you remember your natural deduction, assuming you had a course on that, you might see that syntactically, rules of this sort have the form of introduction rules. And that is exactly right, because remember, for natural deduction, an introduction rule is a way of concluding something involving a certain connective or sign. In this case, the connective or sign is even. So quite literally, the two rules which make up the inductive definition here are two ways of introducing new even numbers. So this is not merely a coincidence of some kind, but it is very fundamentally the same idea as an introduction rule in natural deduction. Now, the minimality part, that is to say, no other numbers are even, or to change language again, to say only those numbers created by those rules up there are even and nothing else. So minimality gives us an induction rule. And in fact, now here it may sound a little odd to you, but syntactically, the induction rule will have the form of an elimination rule in natural deduction. And in saying all that, I guess I'm kind of copying Martin Löf, who when he formulated his type theory, he had certain things which were clearly inductive, and he did use introduction and elimination rules. So in particular, yes, his induction rules were syntactically elimination rules. But in fact, it does make logical sense. Now, you need induction for all kinds of things. So here, I said set of natural numbers, set of even numbers. So many things are defined inductively. So you've all had a course on programming language semantics, not denotational semantics, the other kind, operational semantics, where you have these sets of inference rules. That's an inductive definition. When you define the sentences of a logical formalism from the inference rules of the logic, that's an inductive definition. When you have some kind of state transition system and you define the set of reachable states, that's an inductive definition. Or transitive closure of a relation. Tons and tons of things are naturally defined inductively. And so it's very good that, in fact, almost any proof assistant you adopt today, so even if you run away and say, I hate Isabelle, I'm going to use, you name it, it will almost certainly have good built-in support for inductive definitions. So here is how you do the example I just showed you. So there is a set called EV for even natural numbers. There I give the type, so the type there, nat set. So this is a set of natural numbers, and we have two, so I've even given them names ending in I to kind of scream out to you that they are introduction rules. So one of them says 0 belongs to the set EV, and the other says if n is an EV, then so is the successor of the successor of n, which is of course n plus 2. And then it prints a bunch of stuff underneath in the output window. They're actually debugging messages for me, and we should have got rid of them long ago, but anyway. Now the thing you need to do is prove things about this set. Now, if you remember your operational semantics course, especially for those of you who did it here, or no doubt you had a similar course elsewhere, you may have faced the terrible task of proving things about an operational semantics. And there are always the problem of figuring out what kind of induction to do. Generally, the induction to do very much depends, as always, on the statement you're trying to prove. So what do we say there? 2k belongs to EV. What do we have that we know about? We have k, which is a natural number. We have EV, and we have its rules. That is, we have its introduction rules, which we quoted when we defined it. There is also an induction rule for EV, but we can't do anything with the induction rule. You'll see when we get to an induction example, you need a member of EV to use the induction rule, because the whole point of induction is to exploit the minimality That is to say, if I have an element of EV, then I know it must be 0 or the successor of another element of EV. Here we don't have an element of EV at all. In fact, the whole point of this lemma is to prove we have elements of EV. So it's a good guess before we even start that we will need the introduction rules that we saw on the previous slide. And since we can't do anything directly, you conclude pretty quickly that some kind of induction is necessary on what we do have, which is k. So we do a normal natural number induction, and we get two goals, and they look kind of obvious, in fact, because the first one, 2 times 0, will be 0, which belongs to EV, and the other one, that 2 times suc k, when we simplify it, we will get suc of k, of 2 times k, and then we will have that one as well. So what have I done? I kind of spoke ahead of my slide. So there we did auto and did the simplifications that I just told you. And there I'm just emphasizing, so if you like, I'm being just incredibly explicit here to show you that our sub-goals are almost identical to the introduction rules. And because of that, I can prove it simply using the 2 introduction rules there, which I've done. Now you might, if you're really alert, you might say, this is kind of weird because, as you recall, simplification is about rewriting with equalities. Neither of those theorems quoted is an equality. Well, the simplifier tries to use whatever you give it. So if it sees a thing that's not an equality, but does assert some atomic statement like here, 0 in EV, it will regard that as rewriting that entire thing to true. Likewise, the second rule there, it will see as a conditional rewrite, where if something else rewrites to true, then the conclusion will rewrite to true. So this works. You can also do it this way. So you can use the intro modifier of auto. This is getting into the more esoteric parts of the Isabelle automation, where this is explicitly saying, never mind the simplifier, I want to backwards chain. And this, I think, people find a little trickier to get used to at first, but I think logically speaking, it's actually the more natural way. So when you've got introduction rules, that's why the modifier there is called intro. It tells the prover to backchain using those rules, that is to work backwards from the conclusion to the precondition, and that will prove it as well. See, I'm always doing that to people and it never does me any harm. Okay. Now, I'm wondering about this term rule induction. We use it at Cambridge. I don't know if it's used anywhere else. It just means induction with respect to an arbitrary thing set defined inductively. So here we assume, well, we use induction on an inductive definition when we want to prove that every element of the set that we've defined inductively satisfies a particular property. And that's what induction always does. So normal mathematical induction proves that all numbers satisfy a property. Structural induction on lists shows that all lists satisfy a property, etc. So here induction is showing that every element of the set we've defined satisfies a given property. And again, this is the minimality of the set that is being expressed here. That is, the only elements of the set are those elements that must exist because of the introduction rules we gave when we defined it. I'm going to repeat myself. I'm sure I said this before. You see, mathematicians tend to often don't refer to this kind of thing. So if you're doing let's say, a proof in a textbook about, let's say, a logical proof system or something, they will tend not to refer to inductive definitions in this abstract way, but they will say something like, we're doing it by induction on the height of the derivation or something. So they actually will reduce it to a natural number induction. So this seems to be a thing that mathematicians are used to doing, but that's actually a little clunky and even involves yourself in doing a little arithmetic to show that this thing has a lower height than that thing, which we don't actually need. Okay. Now, as usual, the form of the induction is going to the form of the induction rule, and therefore the form of the induction proof, is exactly going to conform to the form of the original inductive definition of the set. So you had better have some base cases in your inductive definition. If there aren't any, then you've defined the empty set. Congratulations. And for the other rules where you have from one element you create other elements, that will give you inductive steps in your proof. And by the way, there are often situations where we use an inductive definition to define a thing that is not really recursive, but maybe, let's say, it could be defined in some other way, but perhaps there is some kind of pattern in the conditions under which this thing belongs to your set. And an inductive definition is a nice way to express the suitable pattern. Let's say you want the set of all sets that are weird in a certain way, that contain a certain something. Often an inductive definition will be a neat way to write that, even though there will be no inductive steps. That is to say, even though it's never recursive, it never refers to itself, it merely is expressing this weird shape. Do it if you like. And indeed, there are some things that are defined inductively and even have some recursion where you could express the recursion through, say, a recursive function or something. Okay, getting back to our even example, we're going to show the dual of the previous result. Remember, the previous result said everything of the form 2k belongs to the set EV. So the converse of that is to say every element of EV has the form 2k for some k. That's what we're proving here. And again, if you just look at the statement, the thing we're trying to prove, it gives us, we are given an n belonging to the set EV, and we're asked to show the existence of some k. Now, the only thing that we can really do here is do induction on n, because we really aren't given anything else to play with. And this is a natural thing. And when you look at the statement and you say, okay, this is clearly trying to show a property for every n in EV, then the need to do induction on n, would scream at you, actually. And that is the natural way to show this kind of property. So we do induction on n, and you see we refer explicitly to the induction rule there. This is necessary because n will have type nat for natural number, and it will try to do a normal natural number induction unless you override it by specifying the induction rule there. Let's see how this plays out. You do your induction. Again, this is induction using the definition of EV. And remember what the definition of EV says. 0, right? And the other one, suck of suck. So the first sub-goal is to show that 0 has the form 2k for some k, which will be trivial, of course. The second one is to show that suc n has a form 2k. And here we are allowed to assume that already n has a form 2k for some n. If you do auto here, there's not a lot left. What have we got? Can you see? It says we have to show there exists something, some Ka it's called, such that 2 times Ka is equal to that messy thing on the left there, suc of 2k. Now, it's obvious what's needed here, and of course, you might say, why are we being lazy? Why don't we just specify the thing we want, which will be, I guess, suc k. Why don't we just specify it and be done with it? Well, I never like to specify things. I always much prefer having the prover, especially when it's as easy as this. Prover should figure it out. Luckily, so yeah, auto cannot solve. Basically, auto is too dumb to instantiate that quantifier there with the solution. But luckily, we have got something that will do it. So this arith thing invokes a built-in linear, actually it invokes a bunch of different arithmetic decision procedures, and in this case proves our goal for us. Yes, question?
Would the algebra C's work in this case?
No, I doubt it because of the quantifier. So if you can reduce the body of the quantifier to true, then of course you're done. I don't think algebra, I mean, you might find another way of doing it. But as far as I know, arith is probably the simplest. Now I have a slight aside here so that we can just take a look at arithmetic things. We often call this linear arithmetic, although in fact not all decision procedures are linear. However, the most important class, it turns out, for the natural numbers, arithmetic expressions not involving multiplication, or to be very precise, if you do have multiplication or division, they have to be by constants. And something like 2 times n will in fact be replaced internally by n plus n. This then is a problem if you have n times some ludicrously large number, because it probably won't terminate. But in fact, all of these decision procedures are hyper exponential in the worst case anyway. So the only reason we can use them at all is because a lot of our examples are quite tiny. But yes, it's kind of depressing. Every arithmetic decision procedure, and just to remind you, a decision procedure is a thing you call it and it will definitely say yes or no. It will either prove it for you, or if it fails, then it's not provable at all. All of them take hyper-exponential time in the worst case. So there are a number of different decision procedures implemented in Isabelle. Some are for natural numbers and integers. Some cope with quantifiers. There are others for the real numbers. It turns out for the real numbers, you don't even need this restriction to constants. So for the real numbers, you can have arbitrary multiplication and division, and it is still decidable. However, the decision procedures are so complicated and so slow that you shouldn't push your luck. I'm not going to say much. There are some rather obscure proof methods like the sum of squares tool, which you can actually invoke for some relatively simple real number problems involving even general multiplication. But it's a very esoteric area. So a teeny tiny bit of this is built into auto. Not very much, because it would make it too slow. So the purpose of arith is to handle some of the tougher cases, and in particular where logical signs are involved. There was a time before decision procedures. A lot of this stuff happened in the 90s. I can tell you, if you have, see, you're too young to have experienced the tedium of having to correct a punch card over and over again because you had a comma in the wrong place or a space or something and having to wait. It is a little bit like that when trying to prove very simple facts without decision procedures, because if you're in a world where x plus 0 is not the same as x, or even as less trivial things than that, there are often things that are clearly in, equal, say, or maybe the one is meant to be less than the other, where the fact is pretty obvious and yet the necessary rearrangements, and they might involve these assumptions and kind of combining them in a certain way, which are really awfully painful to do explicitly. It could literally take you hours. And when there's a bit of code that just, it's done, that's how we want to do it. So again, almost any proof assistant you use, Koch, Lean, Isabelle, Hall, they will all have something of this sort at your disposal. I do hope to fill all of you with inspiration in these courses. Okay. Let's look at another example. This is actually built in, although not with those names. As usual, I have to rename everything so that the built-in ones don't obscure the thing that we're trying to demonstrate here. So the idea of a finite set is a very simple inductive definition. I think I said on Friday we looked at finite sets from the point of view of their more abstract properties, and now we're going to see how they can be defined inductively. And by the way, if you were watching very carefully, the last time we defined EV as an inductive set, whereas here we're defining FinSet as simply inductive, which means it's an inductive predicate. And I think it's the annoying necessity of having inductive sets and inductive predicates that caused some people to want to identify these concepts for a brief period after 2011 or so. But the fact is, sometimes it's useful to have a set, and on other occasions, especially if you want to define some clever infix syntax and make it all look beautiful, sometimes it feels more natural to make a predicate. So here, the idea of a particular set being finite feels like a property rather than you're wanting to create a set of all finite sets, which maybe feels a little weird. Anyhow, here we go. We say the empty set is finite, and moreover, if I have a finite set A, and I insert a little a into it, and then that is, of course, still a finite set, and there are no other finite sets, so this is simply saying all the finite sets are the kind of thing that you can enumerate by inserting into the empty set. What is this? What did I just do? This is quite a useful thing to do when you define a set inductively. So I mentioned before this intro modifier that you can use with auto, and which will tell it to backwards chain on introduction rules. So when you look at those things up there and you say these look pretty good for backward chaining because they the main thing is, look at the second one. It says to prove that a certain set is finite that has insert in the way it's actually specified, it's enough to show that A belongs to that predicate or satisfies that predicate, which means we are making the argument smaller, and so that looks like a thing where backward chaining would be right. So in fact, with most inductive definitions, it makes sense to do this, and then when you call auto, it will automatically try and backwards chain, and it will prove a lot of things for you. So here, I believe we looked at this theorem last time, and now we're going to see how you actually prove it. So I've got two finite sets, A and B. I want to show their union is finite, and so here, of course, everything is symmetric, but we chose arbitrarily to do induction on the set A using the induction rule. So again, I've named the rule finset.inductive. Remember, you have to do that if you want to do an induction over an inductive definition. And I hope you can see in the sub-goals down below there, it's pretty obviously going to be trivial. So for the base case, I've got to show the empty set union B is finite. And of course, when we simplify, the empty set will go away, and that will be trivial. For the second one, to show that that thing at the very bottom of the slide is finite, when you simplify that expression, the insert little a will come out to the front. Then the backward chaining will say it's enough to show that A union B is finite, and that will all go through. So that was an easy proof. Here's something slightly more interesting. So, if A is a finite set and B is a subset of A, then B should be finite, right? I hope you all believe that. Now here it turns out you need to be a little clever. So I'm doing induction on the set A, which is the only set we have to play with. That is to say, A is the only thing for which we are given that it is finite. Again, I named the induction rule. Now why did I do arbitrary B? Well, we talked about this in something like the third or the fourth lecture, where you need it when your induction hypothesis needs to have the possibility of varying rather than being fixed. It should maybe be obvious, because as we're looking at this induction, we are looking at the buildup of A, and it may well be that you need a different B as a subset of A in order to make your proof work. So what we're going to show here, in a sense, we're going to express a slightly different claim, namely that if A is finite, then every subset of A is finite, and that will allow us to complete our proof. What you see here, so the first one says if B is a subset of the empty set, then it's finite. Well, it's very easy to show that if B is a subset of the empty set, then it is the empty set, and we know the empty set is finite, so we'll be done. What about the other one? Okay, there, because I made B arbitrary, our induction hypothesis has that more general form, so it literally says for every B, which is a subset of A, B is finite. Now I'm looking at a B, which is, you see the last assumption there on the bottom line. B is not a subset of A, it's a subset of insert little a into A. So this is going to be a little tricky. So what did we do? We did auto, and all the easy stuff went away. We are left with, we know that B is a subset of insert little a, big A, and we have our induction hypothesis. It's not entirely clear what we should be doing next. Well, there are two things you could do. I mean, you could think a bit harder, and you could decide for yourself what we want little b to be. And I suspect we would probably do case analysis on, I don't know, whether little a is in B or not, something like that perhaps. I'm not sure. But what we can do instead, you've all tried Sledgehammer already? Most of you, I'm glad. Well, we can call Sledgehammer here. So this is not super easy. This proof, I tend not to like Sledgehammer results that have more than 4 or 5 theorems named in them, because otherwise it's abbreviating really quite a tricky proof, which is not so easy to figure out. That doesn't mean I'm going to actually reject something that has 10 theorems in it. I would certainly wish I could find a different proof that had only 5, but anyway. Here, all of these lines are so long that we can't even see the end of them. But whatever, Sledgehammer proved them. It did it pretty easily in this case. Now, you probably will not see Sledgehammer min anymore. It's very rare now. However, if you do see it, you should try clicking on that. See, normally it does that automatically now. Quite often the thing you get has got excess junk in it, so it will include theorems that are not actually being used in the proof. And Sledgehammer min is a good way of identifying those redundant theorems and chucking them out. So if you do see that is, you see Sledgehammer min there, and if the proofs that you've got are a bit too long for your liking, then click on it and who knows, it might help you. Okay, so this actually, to my mind, is a slightly ugly proof, because you've got your induction, then you've got auto. The reason some people dislike auto used in this way is because you have no idea what it did. So I did an induction, fine, we know what induction does. As for metis, we know that it proves stuff, right? Whatever you give it to, it will be proved or it will never terminate. That's pretty simple. Auto could do absolutely anything. It could reduce one goal to 100. It could reduce 100 goals to 1. It could rewrite them in absolutely any way. So a lot of people will say that you shouldn't do this, and indeed in a future lecture we will look at how you can express inductions in a structured style, so that in that case you could deal with the base case separately, and then in the inductive step case maybe you could be a little more explicit in setting that up so that you're not just throwing auto at it. On the other hand, if I were you trying to get an assignment done on time, especially with a deadline, I would definitely do that at least when finding the first proof, right? You all do this with any kind of assignment or essay or problem. First you write it out, you get the solution, and you covered several pieces of paper with all kinds of horrible kind of crossings out and junk like that. And then you all copy it out neatly again for your instructors, so they will be impressed at how genius you are that you just wrote out the solution perfectly the first time. So that's what you should be doing. Time permitting. I mean, it does affect, your score on the work that you hand in. It's not like I would count that and say -1. It's not like that. But the overall impression of skill and professionalism is going to, as I say, it will be somewhat subjective, but it will have some impact on, mostly on getting the extra score. In other words, if you solve the problem, if you prove the theorem, unless you do something really horrendous in there, you will get the full marks for proving the theorem. This is about getting extra marks above. Okay, I should say a little about how Sledgehammer works. You have your Isabelle session. Now when you click or otherwise invokes Sledgehammer, it takes basically the whole world. So every theorem stored in the system is processed, and a few hundred that are thought to be relevant on various syntactic criteria will then be packaged up and sent to external provers such as those. These days, I can't remember, there's a thing called Verit, there's Z3, maybe one or two others. The selection of provers seems to vary over the years. There was a time when Vampire usually ran on a machine in Miami, but I think not so much these days. By the way, if you are getting this warning from Vampire that you won't run, then you need to tick the non-commercial box in your preferences. So you have to certify that you're not doing anything commercial to run Vampire. Anyway, they go to these provers, and these provers come back with a claimed proof. Now, Isabelle does not believe these proofs. So remember, we have our LCF principle, we have our kernel. So these proofs are actually thrown away. One of the architects of one of these provers was actually shocked to hear this. We throw away the proof, and all we keep is the list of theorems used. So we gave, let's say Spaß, because that's the developer I'm thinking of, we give Spaß 400 relevant looking lemmas. Spaß comes back with a proof using 7 of those theorems. We take those 7 theorems, and then we generate a call to this thing called Metis and ask Metis to prove it with those 7 theorems. So what is Metis? Metis is a general purpose resolution theorem prover that has been integrated with the Isabelle kernel so that when it proves a theorem, its proof really goes through the kernel and is a legitimate proof in the calculus. Metis is nowhere near as clever as Spaß or Vampire. So if you gave Metis 400 theorems, it would never return. But if you give it 7, it can return. The other nice thing is that when you call Sledgehammer, because it takes a while, I think the default setting is 30 seconds, you can up it. Sometimes if I'm really stuck, I will give it you can also type in an explicit command, give it more time, like 2-3 minutes. I find that is most useful when, in fact, the 30-second run gave you a proof, but it was really, really ugly. You can then give it more time, and maybe a different prover will find a more attractive proof. Anyway, while it is thinking away, okay, you could go to the toilet, you could make yourself a pot of tea, but you could also look ahead, go further down into your document and type in stuff there, and it will be fine. What you mustn't do is go earlier in the document, because if you retype stuff earlier, it will then reprocess everything, and the Sledgehammer run will restart from the beginning. But you can do anything you want afterwards. How to get a good result. There's stuff that Sledgehammer is really good at and things it isn't. So firstly, you should never give Sledgehammer something that in its raw form. So try and simplify it as much as possible. Auto is really good for this. So just call auto, and that will do what I said. It will simplify things, it will break them into pieces. Any other simplifications are also helpful. Also, if the thing you are trying to prove has bound variables in it, Sledgehammer is probably not going to be of much use. So it can be helpful if the thing that's critical is inside the variable bindings, if you can somehow extract it, maybe in the form of a separate thing to prove, where you have eliminated. By variable bindings, I mean, let's say you're trying to prove something about a summation or an integral, something where you have a lambda inside the expression. It's not so good there. But very often you might have a thing, let's say I have 2 sets and I'm trying to show the cardinality of one set equals the cardinality of the other. It might be easier to get rid of the cardinality function and say, well, maybe the 2 sets are actually equivalent. maybe they're equal sets. Maybe there is a one-to-one mapping between the two sets. So look at, because by removing that outer function, you might then be able to get inside and maybe get more directly at the sets. If the sets are written using a thing with a bound variable, then you could simply use auto at that point, and then the bound variables would go away and so on. Anyway, there are lots of tips there. I said this already. Sometimes you get not a single metis call, but a long and really ugly looking thing. Most of them don't actually work, but occasionally you'll get one that does work. It's better than nothing, but they really are very ugly, and it would be a good idea to try. Often if you get one of these multi-line monstrosities, if you look inside, you'll see that it proved something useful. It might have proved some intermediate lemma, which if you proved yourself first, you would then be able to get a nicer proof. And it is worth trying to make your proofs look good. Okay, the manual is in your documentation tab, and it's very useful. And as always, if you are stuck, see if there are some other properties of your stuff that could help you on the way. Okay, and that's it for today.